Okay. Yeah, so I didn't give away any of my any secrets in the first half, right? Because I didn't tell you any of the conjectures or any of the results, but this, of course, will now change. So again, the goal will be to explain this kind of analogy between these two things. And then, as I said, I'll also try to say something about symmetries in these Lagrangian fibrations. The way that we can relate those two things, so the topological and coherent things, is by this formalism of Hodge modules. So this is actually what Saito uses to prove the decomposition theorem. Again, this could be a pretty big topic, but I just have, I think, 3 or 4 slides. So I'll just remind you very quickly of some elements of it and then give you one example. Okay. So Hodge modules are generalizations of variations of Hodge structure. And it's the things that you use when you want to study maps between spaces, that when you want to study morphisms with singular fibers, and when you want to apply the decomposition theorem. Okay, so a Hodge module, just like a variation of Hodge structure, has 3 components. First, you have a perverse sheaf, which is the topological component. So this is the thing that generalizes a local system. Then the second component is a D module, curly P. This is, if you like, the analytic component, right? A D module is a sort of gadget that basically encodes in some algebraic way a system of differential equations. And then the third part is the Hodge filtration. So this is a filtration of this D module by coherent sheaves. So this is a coherent object. So it has these 3 elements: a topological, an analytic, and a coherent part. And the way you think about it is as a variation of Hodge structure with singularities. So this Hodge module P will have some kind of support, which will be a closed subset. And on an open subset of the support, it's just the variation of Hodge structure of some weight. And then that variation of Hodge structure is extended in some way to allow for some singularities. The way the weights work, I don't know why I even said this, but anyway, the way the weights work is that the weight of a Hodge module is the weight of the VHS plus the dimension of the support. This is so that the weights behave nicely. Okay? And then once I have a Hodge module, I can make a complex out of it. This is the Ram complex. So this D module has an action by the sheaf of vector fields on it. And using that action by the vector fields, I can make a de Ram complex, right? So for example, I have a map from the D module P to the sheaf of 1 forms times P, where I take a basis for the vector fields, take a dual basis for the forms, and then act by the vector fields. This complex is actually the complexification of this perverse sheaf P. This is the so-called Riemann-Hilbert correspondence. So the topological and the analytic data, they are related by this de Ram complex. And then since I have the Hodge filtration, I can filter this complex, and I can take the graded pieces. So this complex, this de Ram piece, has an increasing filtration, and the graded quotients are complexes of just coherent O modules. They're denoted GRFK of the de Ram complex. And again, they have this sort of shape here. There's certain kind of complexes that use the D module structure to give you a complex of coherent sheaves. The other piece the other object that I can get is I can just take the associated graded of the D module with respect to this filtration, and this gives me a module over the associated graded of the differential operators. And that associated graded of the differential operators is just the symmetric algebra of the tangent bundle. And so I also get a graded module over the symmetric algebra of the tangent bundle. Okay, so these are 2 ways from taking the sort of topological thing, the perverse sheaf or the D module, and getting some coherent stuff out of it. I can either take graded pieces of the de Ram complex, or I can take this whole graded module here. In general, there's just this formalism that says that, you know, these objects here that I get have certain properties. I usually don't know what they look like, except in very simple cases, right? So here's the one case where you can say explicitly what all of this is. There's a constant Hodge module denoted QB of n. Again, B is a manifold of dimension n, right? The perverse sheaf is just the constant sheaf but shifted to make it perverse. The D module is just the structure sheaf with the usual action by differential operators. And the Hodge filtration is just the trivial filtration that is jumps at F0. In this case, the de Ram complex is just the usual holomorphic de Ram complex. the holomorphic forms, right? By the Poincaré lemma, this holomorphic de Rham complex is a resolution of the constant sheaf C sub B. And so this is in a special case of this isomorphism here. And if I take the graded quotients, because the filtration is so simple, the graded quotients are just chopping off the different pieces of this de Rham complex. So if I take the graded quotients, I just get the sheaves of forms at different degrees. Again, the indexing is slightly funny, so there's some shifts and so on, but it doesn't matter so much, right? The graded piece in degree minus P with the usual conventions gives you the sheaf of P forms. And this graded module over the tangent algebra is just the structure sheaf just sitting in degree 0 as a graded module. Okay, so in this case, it's very, very simple. So somehow this explains though where the holomorphic forms come in. So if you do Hodge theory, the holomorphic forms can be thought of as graded pieces of the de Rham complex of this object. And so usually when there's some special properties with differential forms, they're usually explained by thinking of them in this way. Okay, and let me say one more time that we'll be looking not at this Hodge module, but at other ones. But typically, I don't know what these other ones look like, right? There's just this formalism that Saito has that says that I could take a map and push stuff forward and so on. I get these objects, but I don't usually know what they look like. Part of the game is to understand what I can say about them. Okay, and so now with these Hodge modules, I can make a go at trying to relate holomorphic forms on M and perverse sheaves on B. Okay, so this is how I'll explain now. So the simplest case of this relation is actually just Matsushita's theorem. Matsushita's theorem, I claim, actually relates the structure sheaf OM, which C is a graded piece of the de Rham complex here. But anyway, it relates the structure sheaf OM and this lowest perverse sheaf P minus N, right? So here's how this goes. First, Matsushita's theorem said that the push forward of the structure sheaf splits up into the sheaves of holomorphic forms on B. Okay? And we had this explicit process for explaining how the map goes. Now, this Hodge module P minus N, on the other hand, my indexing was such that P minus N has to do with the variation of Hodge structure on the cohomology of the fibers in degree N minus N, so in degree 0. The fibers are all connected of dimension N. The 0th cohomology is just of each of the fibers, including the singular ones, is just Q. So what I get is that this Hodge module P minus N is just Q, just the constant guy. Again, with a bit of decorations to make the weights and the shifts come out correctly, but basically it's just Q. And so this means that if I take the de Rham complex of this Hodge module, and then I take the graded pieces of it, this is another way to get these sheaves of forms. Right, so I could say, well, I can take this Matsushita isomorphism, and now I think of the holomorphic forms on the right-hand side, not as holomorphic forms, as graded quotients of the de Rham complex of this Hodge module P minus N. And then I can write my isomorphism in this way, again with the correct shift. The push forward of omega of OM with some shift splits into the direct sum of the graded pieces of the de Rham complex of P minus N. And so you see now I have a formula that has OM on the left-hand side. This is omega M, where this K is minus N, right? Omega M0. I have that on the left-hand side, and I have my Hodge module P minus N on the right-hand side. And Matsushita is an isomorphism that relates those two things. Okay, so if you want, I mean, there's no mechanism, right? It's probably just all an accident. But anyway, if you want, you can think of Matsushita's theorem as being some relation like this. And so what I have to do to make this relation is, since OM lives on M, I have to push it down to B to get an object on B. And I get a complex of coherent sheaves on the left. And the statement is that that complex of coherent sheaves can also be gotten from this perverse sheaf P minus N by going to the corresponding Hodge module and then taking graded pieces of the de Rham complex. Okay, so this is how you get past this problem that one object is on M and one object is on B. You push down to B, and you have two objects on B. And then the second problem is one object is coherent, the other one is topological, and that's solved by replacing the topological thing by a Hodge module and then taking graded pieces. Okay, and so, I mean, I wouldn't be saying this at this moment if it wasn't sort of like this in general. Okay. So now what are the objects in general? So in general, it's a little bit more complicated. So let's go back to the decomposition theorem. Again, this says that the push forward of the constant sheaf splits up into these perverse sheaves PIs. Well, Saito's theory actually says that each of these PIs is a Hodge module, in fact, of weight I, if I index things correctly. And Saito's theorem also lets me compute the holomorphic, the RAM complexes of these the RAM complexes of these PIs in terms of the push forward of the RAM complex from upstairs, right? So upstairs, for the constant guy QM, the graded pieces of the RAM complex just gives me sheaves of forms. Now, if I can push this down, then I get that the push forward of the sheaf of n plus k forms is the push forward of the RAM complex upstairs. And then one of the results in Saito's theory says that pushing forward and taking graded pieces of the RAM complex, those two operations commute. So I can take the push forward inside, apply the decomposition theorem and replace it by the sum of these PIs, and then I will get the graded pieces of the RAM complex of all of these PIs. Okay, so here, the push forward of the sheaf of forms splits into graded pieces of the RAM complex. However, the indexing doesn't work, right? It's not that one of the omegas goes with one of the PIs. Each omega goes with all of the PIs at the same time. They're all mixed together somehow. Okay, so now here's to simplify the notation, here's a useful definition from this paper by Junliang Shen and what's his first name? Chichen Bin. So these complexes that show up on the right-hand side, the graded pieces of the RAM complex, they took them and called them perverse to Hodge complexes, because you start from a perverse sheaf, take graded pieces, you get some Hodge theoretic objects, and we'll just denote them by GIK. They will show up a lot, so notation will be much simpler if I call them GIK. I can then take this Saito isomorphism here and write it very simply like this. The push forward of the sheaf of n plus k forms splits into the direct sum of these complexes GIK. The GIKs have two indices. I is the index for the perverse sheaf. K is the index for the graded pieces of the RAM complex. And so roughly what these two indexes measure are, I is roughly the degree of the cohomology along the fibers, because the perverse sheaf PI is associated to the n plus ith cohomology of the fibers. And then K is roughly some kind of holomorphic degree, because you see on the left-hand side, the K shows up in omega m to the n plus K. So the two indices are sort of two different things, right? One is kind of cohomology along the fibers, one is sort of holomorphic degree. Okay. And so what I want to say is, before we get to the complicated bit, so these complexes GIK, they're very hard to understand in general at the singular points. At the smooth points, when the fibers are just abelian varieties, they're extremely simple, right? If I go, so let me explain this on this slide. If I take the smooth locus of pi, everything is very simple because the fibers are just abelian varieties. So the Hodge modules restricted to the smooth locus are just variations of Hodge structure. And we already computed the Hodge bundles. They're just these wedge powers of the tangent and cotangent bundle. And then you can write out this complex GIK explicitly. It's just, again, the RAM complex for this variation of Hodge structure. And what you end up getting, if you keep track of the degrees correctly, is this complex here. It starts with K forms on B times the Hodge bundle in degree n comma I. And then you increase the degree for the K forms, and you differentiate on the Hodge bundles, right? So the map here is just given by the Gauss-Manin connection, the derivative along the fibers. If you look at this complex here, you see that, again, I and K have different roles, right? K is sort of the holomorphic stuff again. I is the fiber degree, but the complex is actually symmetric in I and K. For example, the first term is really omega K times wedge n of TB times omega I, and I could swap I and K and it would be exactly the same thing. And in fact, in the paper by Shen and Yin, where they introduced these complexes, they observed already that GIK and GKI are actually isomorphic as complexes. over the smooth locus. And the isomorphism is really just the one that swaps those two things, basically. And then they were making a prediction about what should happen at the singular fibers. And their prediction is, in terms of these complexes, that GIK and GKI should always be isomorphic, including at the singular fibers. They will not be isomorphic as complexes, though. They gave examples where that fails, but they should always be isomorphic in the derived category. This is, again, some kind of symmetry that sort of swaps holomorphic and coherence, holomorphic and topological stuff, right? Because we said I is cohomology degree and K is a holomorphic degree. So if I can swap I and K and get the same object, it says that there's some symmetry between holomorphic and topological stuff. So this is also something that we'll want to explain, this kind of symmetry in these complexes. Okay, so now let me really get to the sort of main theorem. So the relationship between the forms and the perverse sheaves. This goes to the following construction. So what you can do is, from both of these objects that I want to relate, you can construct modules over some algebra that I'll call omega B. This algebra omega B is just the algebra of holomorphic forms on B. But for some technical reason, I guess it would be good to do it in a sort of derived sense. So this is some algebra where each of the terms in the algebra actually has a shift in the derived category. And when you multiply, the shifts get added together. So this, I mean, the algebra is really just sort of the wedge algebra where you just wedge forms together, but you just place them in different degrees, okay? Then it will make the indexing easier. Okay, so the observation is, if I have a D module with a filtration, then I can take the graded pieces of the Ram complex, and in there you see holomorphic forms show up. If I take the direct sum of all of these graded pieces, I can actually make it into a complex of modules over this algebra omega B, basically by just wedging with the forms, right? So you see here, for example, if I take the first sheaf in this complex GRFK, and I take something in the degree 1 here, so a 1 form, then I can multiply those two things together, and I will go into omega 1B tensor GRFK, which will be the graded piece in degree 1, which will be the next term in this complex, but where K gets replaced by K minus 1. So if I take all of these complexes together, then this omega B will act on them naturally. And so the direct sum of all of the graded pieces of the Ram complex, I will denote that by BGG of GRF dot of P. This is actually a complex of graded modules over this algebra omega B. To make it graded, to make the grading work out correctly, you have to put a minus sign here, but never mind. So anyway, the map is just basically, you just wedge with the forms and you do nothing to the P part. And in fact, this functor, or this operation here, I'm calling it BGG because this is known as the BGG correspondence. The B is Bernstein, and the two G's are Gelfand Jr. and Gelfand Sr. And this shows up in a paper of theirs about vector bundles and projective space, right? In fact, what this operation does is it takes a graded module over the symmetric algebra and constructs from it a complex of graded modules over this algebra omega, which is really like a wedge algebra. And their theorem is that in the derived category, the modules over the symmetric algebra and modules over the wedge algebra are the same thing, basically. So if I take this sum of all the graded pieces of the Ram complex, with this module structure is actually the same information as the associated graded for the filtration. Okay, and so this operation I can apply to my Hodge module. So I can take my Hodge module PI. Instead of the topological part, instead of the perverse sheaf, I look at the D module. I take the associated graded with respect to the Hodge filtration. This gives me this module over the symmetric algebra. And then I do this BGD correspondence. So I take the direct sum of all the graded pieces of the Ram complex. This is now a complex of graded modules over this algebra omega B. If I write them in terms of the perverse Hodge complexes, it looks like this. It's the direct sum over K of the GIKs shifted by I. Okay. So this is the first side of the story. So from my perverse sheaf, I go to the D module and then I construct this complex of graded modules. And now what happens is that I can also construct a complex of graded modules from the other gadget, from the sheaf of forms. And this operation is what we'll relate the two. Okay, so from the sheaf of forms on M, I can also build a complex of graded omega B modules. And this again goes through Matsushita's theorem. Namely, what I can do is, so omega M is of course a module over OM, right? If I push it forward, like I did earlier, R pi lower star omega M, this will be some kind of module in some kind of derived sense over the push forward of the structure sheaf. But the push forward of the structure sheaf is actually, even as an algebra, is this algebra omega B by Matsushita's theorem. And so you see naturally, at least in some kind of derived sense, the push forward of the forms will be a module over this omega B. It will not be graded, but it will be some kind of module. And then what I can still do, so this is a step I'll be a little bit vague about, I can take some kind of associated graded of this complex. This complex, this push forward complex actually has a natural filtration called the perverse filtration from the decomposition theorem. I can take the associated graded for that filtration, and then I will actually get a complex of graded modules over this omega B. And if you write it out, the associated graded is actually the direct sum of these, again, these perverse Hodge complexes, but where now the K and the I are swapped. Now it's GK, I. Right now I'm fixing the holomorphic degree I, and I'm just letting the first index vary, right? This formula here that I'm using is just this formula from this Saito formula here for the push forward of the forms. Okay, so from the D module, I can make a complex of graded modules over omega. And from the sheaf of forms, I can also make a complex of graded modules over omega. And then the main result is that those two things are the same. So that's the relation that we were looking for. Okay, so it says for every I, there is an isomorphism between these two objects in the derived category, and it is compatible with the grading on both sides and also with the structure of omega B modules. This is the relationship. Okay, so you see it's a little bit more complicated than just looking at coherent things. For example, if I just take the left-hand side as in the derived category of coherent O modules, I don't have enough information to recover the right-hand side. What I need is this extra module structure over this wedge algebra. But once I add that, then it's good. So on the left-hand side, I started from the holomorphic forms. On the right-hand side, I started from the perverse sheaf, so that's good. And actually, on both sides, I also took some kind of associated graded, which is maybe interesting. On the right-hand side, I didn't directly take PI, but I looked at the associated graded for the filtration on the D module. So this is some kind of associated graded for the Hodge filtration. And on the left-hand side, to make the module structure correct, I also had to take an associated graded for some perverse filtration. Okay, so this is again a sort of different filtrations on the two sides, but again, the same kind of operation happens on both sides. Okay, so does the statement make some sense? Any questions on it? It's rather complicated, right? You see, I mean, this is why I didn't really feel like giving the statement even in the first half. But you see that in order to even formulate this is not something that happens on the sheaf level, right? In order to formulate this, I have to go to the derived category. I cannot see this just on complexes or something. And then I have to go not just to any derived category, but to the derived category of things that have this module structure. So this is a somewhat intricate. It's a somewhat intricate thing.
So where does the Hodge module come from on the right-hand side?
So the PI is the Hodge module that I get from the cohomology of the fibers in the Lagrangian fibration. Right, I have the Lagrangian fibration pi from M to B, and I take the n plus I cohomology of the fibers. Okay. Yeah. Okay, so on the right-hand side, I'm really using kind of topological stuff because this sees all the cohomology of the fibers in some degree. On the left-hand side, I'm only seeing the sheaf of n plus I forms reciprocal fibers. Any other questions on the statement? I won't tell you the proof at all. So because the proof is again somewhat complicated. You can look at my paper. Like I try to write a sort of nice summary of the proof in the introduction, but so maybe just in 2 sentences. So what the idea is that you want to show this statement for every I, right? But it's difficult to show it for any particular value of I. So what you do is on both sides, you take the direct sum of all of the objects. On the left-hand side, you take the sum over I. On the right-hand side, you take the sum over I. And then it turns out on that direct sum, you can perform some kind of rotations that are sort of like hyperkähler rotations, if you know what I mean. So you can act by the symplectic form in some way and kind of think of that as kind of rotating the module structure in some way. And you can also act by the Kähler form that again gives some kind of rotation of the module structure. And it turns out that, so if I take the direct sums on both sides, I get the direct sum of all of these complexes GIK over I and K. And these sort of rotations coming from the holomorphic symplectic and the Kähler form, they turn out to rotate the module structure on one side exactly into the module structure on the other side. That's roughly speaking is the idea, right? So just like in Matsushita's theorem, where you do these 2 operations of first contracting with sigma and then contracting with omega, the same kind of stuff happens here. But if you keep track of the module structures, you actually see how one of them gets transformed into the other. Okay, anyway, so this sort of accomplishes the goal of relating those 2 objects, but of course in a kind of complicated way, right? And so now what I want to do in the last part of the talk is I want to explain what this says about symmetries of Lagrangian fibrations. So I claim that this statement, even though it's somewhat technical and somewhat hidden, it actually contains inside of it some very interesting, very unexpected symmetries for arbitrary Lagrangian fibrations. Okay, so this is what I'm going to talk about in the rest. Okay, so let me first say one more time, slightly more precisely, this conjecture by Schnell and Yin. So in this main theorem here, both the left-hand side and the right-hand side can be actually expressed in terms of these perverse Hodge complexes, right? For the right-hand side, by definition, because I'm taking the sum of the graded pieces of the ground complex. On the left-hand side, by the Saito theorem. So actually, the main theorem, in terms of these perverse Hodge complexes, it says that those 2 sums are isomorphic, but where the 2 sides have 2 different module structures, right? So you see that on the left, I'm summing over K on both sides, but in one case, it's really the second index, and in the other side, it's the first index that's being summed over. And Shen and Yin, remember, they show that over the smooth locus of pi, GIK and GKI are isomorphic as complexes. And they conjectured that in general, they should be isomorphic in the derived category. One byproduct of the main theorem is actually a proof of this, that in fact, GIK and GKI are always isomorphic in the derived category of coherent homologies. Shen and Yin didn't really come up with an explanation for the symmetry, right? They were able to show that on the smooth locus, the 2 things are the same, really by an explicit sort of operation that swaps 2 things. And then they computed some examples that show that over the singular locus, it's kind of more complicated. But in some simple examples that the things still match up, but there isn't really a good explanation for why they match. But the main theorem actually gives a very nice explanation for the symmetry. So we'll see that there's actually a whole sort of collection of symmetries, some of which are very meaningful. And as a byproduct of these symmetries, we will get this ability to swap the first and second index. Okay, and so these symmetries have to do with hard Lefschetz. So there's hard Lefschetz. I already said that. The relative version of hard Lefschetz for the fibers of the Lagrangian fibration. If I say this in terms of these perverse sheaves Pi, I could say it like this, that I have the perverse sheaf Pi, and then the corresponding Hodge module. This is the cohomology in degree n plus I of the fibers. I can wedge with the Kähler forms, and I will go to cohomology in degree n plus I plus 2. In terms of the purpose sheaves, I go from pi to pi plus 2. And the relative hard Lefschetz theorem says that p minus I and pi are isomorphic by wedging with the Kähler form I times. In terms of these Hodge modules or D modules and filtrations, it's this kind of isomorphism. Right? It also changes the filtration because the form, of course, is a form of type 1,1, and so the Hodge filtration gets changed. I can take the relative hard Lefschetz theorem and write it in terms of my purpose Hodge complexes, the GIKs, right? So what it will say is the graded piece for P minus I and the graded piece for PI will be isomorphic. And there'll be some shift in the filtration, so there'll also be some shift in the second index. And so if I write it out precisely, it says that G minus I comma K will be isomorphic to GI comma K plus I, and then an extra shift. Okay, so hard Lefschetz says there is an isomorphism of complexes between those two particular perverse to Hodge complexes. Again, this is a way of stating this relative hard Lefschetz theorem, and I remind you one more time that the relative hard Lefschetz theorem is one of the most difficult results in Hodge theory. It's the thing that gives you the decomposition theorem and all of that stuff. So there's some pretty deep analysis behind this thing, right? So this is not something that if I ran into this somewhere, suppose this hadn't been proved and I ran into the statement, I could conjecture it maybe, but I would never be able to prove it. If these really great analysts hadn't come along and hadn't done it for us, this would be impossible. But so this is very difficult, but fortunately it's done. Okay, now interestingly, it turns out that there's a similar thing that I can do with the symplectic form. That this relative hard Lefschetz theorem turns out to have an exact analog. So let's look at the symplectic form, right? Again, the symplectic form is a closed holomorphic 2 form. So it's a class in H2 in particular. I can still act on the cohomology of the fibers with wedge product. However, the symplectic form, because it's a symplectic form, it restricts trivially to the fibers. So I won't get anything by saying map the cohomology of the fibers to the cohomology of the fibers in degree 2 higher. That map is 0 because sigma restricted to the fibers is trivial. But I do have the decomposition, right? So actually, I can take the entire derived push forward of the constant sheaf, split that up, and see how sigma acts on the decomposition. And so at least in the derived category, the topmost piece where I just act on the fibers, that's trivial, but I have the whole decomposition, and probably sigma has some pieces of lower order in that decomposition. And so the next kind of piece that I can look at is this piece that I will call sigma 1, that kind of acts only of degree 1 along the fibers, and if you want, sort of degree 1 also along the base, right? When I restrict sigma to the fibers and I act by degree 2 along the fibers, that's trivial, but then I can take the next best thing, which is sort of degree 1 along the fibers, degree 1 along the base. And so this will be a map that looks like this, that maps pi to pi plus 1, but with a shift, and then it changes the degree of the filtration by -2, because now this is a holomorphic 2 form, right? Omega was a type 1,1, so you decrease the F degree by 1. Sigma is of type 2,0, so you decrease the F degree by 2. And in terms of my complexes GIK, I get a morphism that now goes from GIK to GI plus 1, K plus 2. And well, what turns out to happen is that just like in the case of the Kähler form, this morphism also gives me a relative hard Lefschetz theorem, which I will call the symplectic relative hard Lefschetz theorem, because it's for the symplectic form. So it says if I swap I and K, if I look at the effect on the second index, then sigma 1 to the K is also an isomorphism. Now it goes from GI minus K to GI plus K. Okay. So the relative hard Lefschetz theorem, which is this difficult topological statement, it has an analog for the action by the symplectic form, the symplectic relative hard Lefschetz theorem. And I have one little slide to sort of say how it's related to the main theorem. So, what I do is I look at the action by the symplectic form up on M. there I know that forms in some degree and forms in the complementary degree are isomorphic by wedging with sigma. So I can push that forward. I'll get an isomorphism between the push forward of omega n minus k and the push forward of omega n plus k. And I can decompose sigma using the different pieces in the decomposition theorem. I get different components in here, and the sigma 1k is sort of the topmost component that shows up. So you have some kind of big, complicated isomorphism between these two things. And there's one particular component in this isomorphism that is sigma 1 to the k. And from the fact that this big, complicated thing here is an isomorphism, I want to kind of get that just this one particular component is also an isomorphism. So it's sort of like I have some big, complicated matrix, which I know to be invertible. And then I want to know that some particular small submatrix is also invertible or something like that. But so the way you do this is you look at this isomorphism given by sigma to the k, you decompose both sides into these complexes g, I, k, and then you analyze what this decomposition looks like. And then you find that you can't quite deduce that sigma 1 to the k is an isomorphism. But if you happen to know that some of the GIKs and some of the GKIs are isomorphic to each other, and this particular statement here turns out to be enough, then you can combine it with this isomorphism and sort of peel off the main component that you're interested in, the sigma 1 to the k. So actually, the symplectic relative Hard-Lefschetz theorem turns out to be equivalent to the fact that this particular sum is isomorphic to this particular sum in the derived category of O modules. Okay, this is just sort of playing around with complexes and maps between them and so on. This is not complicated, it's just linear algebra, but you have to write out both sides and write the sort of map between them in matrix form, and then look at sort of which entries in the matrix are zero and non-zero and analyze it. But this is good because the main theorem, of course, says exactly that those two things are isomorphic, right? The main theorem says that the left-hand side is the push forward of omega, the right-hand side is this BGG complex for the perverse sheaf. And I know that those two things are isomorphic, not just in the derived category, but even together with the module structure, this omega B module structure. If I forget the omega B module structure, then they're just isomorphic in the derived category, and that's enough for this purpose. Okay, so I can get my symplectic Hard-Lefschetz theorem from the main theorem and the fact that the symplectic form upstairs has the Hard-Lefschetz property. Okay, good. So now I have two symmetries, right? I have the symmetry from the Kähler form and the symmetry from the symplectic form. And so now again, I want to, since if I write it like this with these indices, it's very hard to see what they're doing. So I'm going to put it in a picture, just like I did in the case of the Hodge diamond. So what we actually have is we have these complexes GIK. I can go from -n to n, and k can go from -n to n. So I can arrange these complexes GIK on this kind of square grid here, right? Maybe I is the first index and k is the second index. And the way those two maps go is omega increases I by 2 and increases k by 1, and sigma increases k by 2 and increases I by 1. So then these morphisms omega 2 and sigma 1, in terms of this diagram, they give you these two sorts of arrows here. Okay, and I know that somehow if I do omega a certain number of times, I get some kind of Hard-Lefschetz symmetry, and if I do sigma a certain number of times, I get some Hard-Lefschetz symmetry. Again, this is not so apparent from this picture, but it's actually, it turns out to be very, very easy if you draw the picture differently. So first, it is actually true that GIK vanishes in a slightly bigger range. So I and k can be at most n, but also the difference between I and k can be at most n. So this is, it follows from this isomorphism here. This was the isomorphism from Saito's theory. If you look at the formula for the de Rham complex, you also get some constraints from the formula in the de Rham complex. And that means that the terms in this corner here, the complexes in this corner actually also vanish. Okay, so there's actually 3 constraints. So then you see that the natural way of drawing this is not really on a square grid, because this shape here is not a square. But it would be much more natural if I if I sort of distort the grid slightly and make it look like a hexagon. So actually, if I put my complex GIK not at the point I comma k, but I put it at the point I times the root of a third root of unity plus k, then these things naturally form a hexagon. And the three constraints really are just the three opposite sides of the hexagon. And then my two red arrows also become much easier to visualize. So the omega, in the hexagon picture, the omega just moves me up vertically. Right? It increases I by 2 and k by 1. So it just moves up. And this, the hard Lefschetz symmetry, the relative hard Lefschetz for the Kähler form, is now just the symmetry which is reflection in this diagonal. Right? And for sigma, well, for sigma, it goes like this. So sigma goes over like this. K increases by 2 and I increases by 1. And there's the relative hard Lefschetz for the symplectic form then becomes reflection in this second diagonal here. Okay, so the Kähler form is this reflection, the difficult relative hard Lefschetz. My symplectic relative hard Lefschetz becomes this reflection. And so altogether, I actually get 3 reflections, right? Because if I can reflect in this diagonal, and I can reflect in this diagonal, then of course I can compose these and I can also reflect in the other diagonal. And the reflection in the other diagonal is exactly the one that swaps I and K. So this reflection here is the explanation for the Shen-Yin symmetry. It's just reflection in the third diagonal, right? So if I want to swap those 2 points, I go here to the point IK, I do reflection. I don't know, maybe I should annotate this a little bit. So if I want this point here, first I reflect in this diagonal to get this point. Then I reflect in this diagonal to get this point. And then I reflect in this diagonal again to get this point. Right? So the third diagonal is part of is generated by the reflections in the other 2. So this is nice because it's a very conceptual explanation for this Shen-Yin symmetry, right? In their paper, remember, they didn't even propose a mechanism by which this kind of symmetry could come about. But you see that it's a consequence of the 2 relative hard Lefschetz theorems. The classical relative hard Lefschetz from analysis and the new relative Lefschetz for the symplectic form. If you combine them, you get this symmetry explained. And you also see why you need to go to the derived category in order to do this, because the symplectic relative hard Lefschetz only happens in the derived category. Okay, so does this make sense here, this picture? So this is, if you want, some kind of Hodge hexagon. It's not a Hodge diamond, but it's a Hodge hexagon. Mind you that these dots are not vector spaces, right? Each of these dots is one of these complexes GIK, which is an object in the derived category. So this picture is not a picture of vector spaces, but it's a picture of objects in the derived category. Okay, so now we're going to repeat this quiz from earlier. So the same kind of thing we did for the Hodge diamond, right? So I have my 2 reflections, the one in the diagonal from hard Lefschetz, the one in the other diagonal from the symplectic hard Lefschetz, and the Shen-Yin reflection in the third diagonal. Again, these reflections will generate some kind of group. Can you see what sort of group is generated here? Right, so for example, suppose I take this point here, right? So where can this point go? Well, I can reflect it down here. I could reflect it over here. But I can, for example, I can never reflect it to this point, right? So for example, this point here under this group generated by the reflections will have an orbit of size 3. I won't get all the corners, I'll just get these 3, for example. Does this help you sort of tell what group it is? Anyone? Make a guess. Come on, someone. Oh, here's something in the chat.
Yeah.
No, it is not. It is not D6. See, because I can't get all the corners. For example, for D6, you would also say again.
S3.
It is, yes, very nice. It is S3 exactly. So it's just a symmetric group on 3. The two reflections are like the 3 reflections are like the 3 elements of order 2 in the symmetric group, right? Okay, the obvious next question is, since we already saw earlier that Lie algebras kind of show up, S3 is generated by reflections. It is also a Weil group. Do you know what the corresponding Lie algebra is? The Lie algebra whose Weil group is S3.
It is A3.
Well, I guess A2. A2 would be the right name. Yeah.
L3, right?
Yeah, A2, right? So SL3, exactly. Very good. So it is SL3 in this case. Okay, so it's sort of different from the compact case, right? In the compact case, we had the dihedral group and the special orthogonal Lie algebra. In this case, we get the symmetric group because that's sort of the symmetry group of the hexagon that's relevant here, or part of the symmetries of the hexagon. And well, the corresponding Lie algebra is SL3. But anyway, if you take the philosophy from the compact case, this again suggests that this Lie algebra SL3 should somehow show up. The fact that we get these symmetries here and that we get the symmetric group, it should just be a shadow of the fact that there's some Lie algebra action. And again, this is something that one can actually show. So the statement is a little messy looking because these are objects in the derived category and omega and sigma act as a kind of shift, but except for the shift, it's saying that the direct sum of all the GIKs is naturally some kind of representation of the Lie algebra SL3. I need to put this shift because both omega 2 and sigma 1 change the degree by 2, change the cohomological degree by 2. So the shifts make it work out correctly. Okay, so in fact, this whole picture and the reflections here are just a shadow of the fact that there's naturally a representation of this Lie algebra SL3, but it's not a representation on a vector space, it's a representation on an object in the derived category. And again, so this is showing the general idea that I said at the beginning, that when you take omega and sigma together, you will get some interesting symmetries that you didn't see before that. In this case, it's this SL3 symmetry, right? I mean, again, if I just take the Kähler form and I just take the usual relative Hart-Lefschetz, I get an action by the Lie algebra SL2, just like in the compact case. But if I throw this together with the relative Hart-Lefschetz for the symplectic form, then I suddenly get a completely different Lie algebra than the SL3. And I think I have probably 1 or 2 more slides. Just very vaguely what kind of things you have to do to show this. So when you try to show that the Lie algebra acts on something, one way is to just say, well, okay, the Lie algebra is this set of matrices, and for each matrix, you say how it acts. This is not how this kind of thing works. For these geometric Lie algebra actions, you always have the Lie algebra given by generators and relations, the so-called Serre relations, coming from the Dinkin diagram. And then you have a certain set of operators that correspond to the generators of the Lie algebra, and you have to check that they satisfy the correct kind of relations. Right? To show that something is a representation of SL2, you need an operator, you need some grading, an operator that increases the degree by 2, an operator that decreases the degree by 2, and some relations. And here again, it's the same kind of thing. There's certain relations that have to be satisfied. Each of the 2 relative Hart-Lefschetz theorems gives me 1 copy of SL2. For example, the relative Hart-Lefschetz for the Kähler form gives me a copy of SL2 where the grading is by the I, the index I in the GI case, and where the nilpotent matrix acts by omega 2. And then there's a third element that's traditionally called Y sub whatever. So in this case, Y sub omega 2. That's the third element in this SL2 representation, right? Similarly, so this would be like sort of the adjoint of the Lefschetz operator or something like that. Similarly, my symplectic relative Hart-Lefschetz gives me another copy of SL2, where the grading is by K, the nilpotent element is now the action by sigma 1, and then again, there's a third element that I call y sub sigma 1. And the sort of relations that you have to check to get SL3 is you have to check that omega 2 and sigma 1 commute, and you have to check that y omega 2 and y sigma 1 commute. Omega 2 and sigma 1 obviously commute because they're just the top graded pieces of the action by the two forms omega and sigma. And of course, omega and sigma commute because they're just two forms on M. Wedge product with omega commutes with wedge product by sigma because two forms commute because they have even degree. Right? The difficult thing is to get the third elements in these SL2s to commute with each other. This is a very non-obvious thing because this third element is constructed from the other ones in a kind of indirect way. And so in order to get SL3, you have to prove that those two third elements commute. And the way that's done is, again, just to say the slogan, you use the symplectic relative Hart-Lefschetz theorem, and you do some computations with differential forms. So roughly, you look at the action by the Kähler form and the action by the symplectic form and various conjugates of them. There's some relation among certain differential forms and vector fields on M. And then you take, you let that act on the cohomology of the fibers, and you take the top graded piece. And then together with the symplectic relative Hart-Lefschetz theorem, the top graded pieces come out to be this y omega 2 and the y sigma 1. And for that reason, they end up commuting. Okay, so this is basically something about differential forms. But to get the conclusion that I want, I do need to put in my symplectic relative Hart-Lefschetz. And so it is actually also a consequence of the main theorem in the end. It's not directly visible on the total space without these auxiliary results. And then, yeah, I had one last sort of picture here. So once I know that I get SL3, I can actually then explain this curious analogy in the first part. So why is it that both omega and sigma actually satisfy a Hart-Lefschetz property, right? This is something that we observed earlier. Well, I did partly explain it because I showed that omega, the Hart-Lefschetz for omega is the relative Hart-Lefschetz for omega is this analysis result, and the Hart-Lefschetz for sigma is my relative Hart-Lefschetz theorem. But the situation is actually a little better because I do have this explicit symmetry here, right? I have this reflection in this diagonal that changes ik and ki. And things should be a little bit better that omega 2, the action by omega 2, actually increases I by 2 and increases k by 1. So it's this arrow here. The action by sigma 1 increases I by 1 and increases k by 2. So it would be very nice if they didn't just both satisfy Hart-Lefschetz, but in fact, if the reflection in this diagonal actually exchanged Hart-Lefschetz for omega against Hart-Lefschetz for sigma. If when I flip in this diagonal, this red arrow actually becomes literally that other red arrow. That will then really explain one Hart-Lefschetz in terms of the other, right? We will say that under the symmetry and yin, Hart-Lefschetz for omega really goes to Hart-Lefschetz for sigma and vice versa. And this turns out to be true as well. So the relation that you have to prove to get this Lie algebra SL3, this is actually equivalent by just the representation here of SL3 is actually equivalent to saying that I have these two copies of SL2, and then I have this extra reflection that exchanges one nilpotent element in one copy against one nilpotent element in the other copy. So again, having this reflection here take one red arrow to the other red arrow, in terms of algebra, this is equivalent to having the two copies of SL2 together generate SL3. Okay, this is a little exercise that one can do. The relations for SL3 exactly come down to saying that when I reflect and reflect and reflect, in order to go to reflect in this diagonal, then I'm actually exchanging those two arrows. Okay, so from my point of view, this SL3 representation really contains inside of it an explanation for the analogy in the first part, which is why is there a symplectic Hart-Lefschetz that mirrors the usual Hart-Lefschetz? Okay, and so on that end, on that note, I will end here. I'll thank you for your attention, and yeah, thank you.